And welcome back. We're going to tie up some of the things we've been looking at with electrolysis and look at how electrolysis is used in industry. Hopefully this will start to put some of the bits and pieces together, remembering that we've looked at electrolysis of molten solutions and electrolysis of aqueous solutions, considering the different products that we would get in each. Each of these different techniques can be used to produce different chemicals in industry, which is where we tend to see these processes used the most outside of the recharge processes for our secondary cells. So when we're talking about electrolysis in industry, it's usually to produce particular chemicals. Electrical energy is expensive to produce. We know this because of the lack of efficiency we see in most fossil fuel-based generations of electricity, so 20 to 30%. And we don't want to spend too much money producing chemicals that are going to be sold for cheap. So not a lot of chemicals are produced in industry from electrolysis. It's used for using ones that we can't obtain any other way. Okay, so remembering we're converting electrical energy into chemical energy to create non-spontaneous reactions to occur. And this means that the products are non-naturally occurring products, ones that we can't mine or find naturally in our environment. These include things like sodium, metal, aluminium, and chlorine, all of which are a bit too reactive to find in their non-oxide forms in the Earth's crust. So all of these elements are in demand in industry for quite a large array of purposes. So because they don't occur naturally, we have to be able to synthesize them or produce them on an industrial scale. In order for production of chemicals to be viable for commercial production in electrolysis, we need to consider a number of things that can complicate the costs of the production. So when we consider this, we need to consider the locations to be able to have access to cheap and abundant, reliable electricity, because we're going to need that for the process. The electrolytes should be cheap and readily available. There's no point having an expensive electrolyte to then go through an expensive process to get our chemicals if it can be avoided. The electrodes should be inexpensive where possible. So primarily we want to be using things like carbon or iron electrodes, avoiding things like platinum, which are very costly. They want to be located in places to allow cheap transport of materials and products. So remembering that even when we're talking about this, because it's on the industrial scale, we need to be able to get our products somewhere to get them to market easily. We want the electrolysis to be able to operate continuously without stopping to remove product or add reactants. So some way that we can siphon off our products from the electrolysis reaction efficiently without having to get it cooled down or stop the process in order to harvest our products. Where possible, lower temperatures to reduce the heating costs and wear on equipment, and to consider the environmental impacts of the materials that we're using. So these are all things that need to be considered for our commercial process. The first one that we're going to look at, we don't need to know these cells in detail anymore. If you look at older exams, it was needed to memorize each of these cells. But you should be able to identify the anode and the cathode from a given description and the products, and therefore the half equations that are going to occur. Sodium is produced in what we call a down cell, and it is constructed to minimize the contact between the two products. Another thing that we need to remember is that the product of the non-spontaneous reaction, that i.e. what we get from the electrolysis, is the reactant of the spontaneous reaction or the galvanic reaction. So we need to have separation of the products in these cells, or what we will see is the formation of the spontaneous reaction in reverse. You can see from this that this cell is using sodium chloride. This is molten sodium chloride. Okay, so it's NaCl liquid. This means no water is present. It is just very hot molten sodium chloride. We have an iron cathode, which is cylindrical, and then molten sodium chloride or calcium chloride mixture. Usually we see mixtures in industry in order to lower the melting point. The screen is used to prevent contact between the CO2 gas that is going to form at the anode and the sodium formed at the cathode. Remembering this is electrolysis, we're going to start with Na plus and Cl minus. Sodium cannot be oxidized any further, so it will be reduced at our cathode, forming sodium liquid because this is molten. We're going to have 2 Cl minus, giving Cl2 gas plus 2 electrons at our anode. Overall, we will have 2 sodium ions plus 2 chloride ions, giving 2 sodium liquid and Cl2 gas. The molten sodium will actually rise, it's less dense and can be siphoned off, and the chlorine gas is tapped out of the reactor. Aluminium we use in a large number of construction and manufacturing needs. It has a low density and high strength, and we can modify its properties to different applications. You may remember that we talked about this in Year 11 through alloying of our metals. Generally, this is obtained via the electrolysis of aluminium oxide, alumina. We mine a lot of alumina in Australia. Aluminium will react with oxygen over time, forming a white oxide layer, which you may have seen. It has a very high melting point, alumina, so it is dissolved in molten cryolite, which is a sodium aluminium fluoride compound, before electrolysis to keep its melting point down to 950 or 1000 degrees so that it's easier to run this equipment. This is the type of cell that we see. As you can see here, we have large blocks of carbon anodes. These will actually be consumed over time. You can see here that our carbon is going to CO2. So we will have the carbon solid going directly to CO2. So the carbon will need to be replaced. So these are large blocks of carbon that can be lowered into the electrolytic system and easily replaced because they're cheap. So the oxygen produced at the anode reacts with the carbon and produces carbon dioxide. So we have regular replacement, but these electrodes are much cheaper, so we continue to use them. The alumina is pumped in, and we have this molten mixture of alumina in cryolite. So this gives us our aluminium 3+. Okay, so we have the aluminium 3+ plus 3 electrons giving us aluminium liquid. Again, remembering in molten systems, our state will always be liquid because these are going to be molten. And if it's molten enough to dissolve the ionic compound, it will certainly be molten for the metals. At the anode, we have oxygen, O2 minus, going to O2 gas plus 4 electrons. This subsequently goes on to react with the carbon to form carbon dioxide in the consumption of the anode blocks. Okay, as I pointed out before, we don't need to know these cells specifically, but you should be aware of looking for things like the carbon electrodes, paying attention to the polarities here. We can see that these are marked as positive, so in an electrolytic process, these are going to be our anodes. The molten aluminium is denser than the ionic solid, so it is tapped out from the bottom via a vacuum siphon, and then carbon dioxide is released and will be captured for use to make things like dry ice and other processes in the food industry and other industries. For chlorine, again, this is a very reactive gas, but it is used widely in industry for pesticides, polymers, water treatment, all kinds of things. We can produce it in the down cell with sodium, but we tend to want more chlorine than that, and it's more efficient by producing with brine. Brine is a saturated or a highly concentrated sodium chloride solution. We also get sodium hydroxide produced in the cell with chlorine, which is great because sodium hydroxide, again, has a large number of industrial uses. So both products from this cell are useful in industry. The key to remember with this one is that the closeness of chlorine and water on our electrochemical series. Remember, the strongest oxidant will react with the strongest reductant. The strongest oxidant in this case is going to be water. So it will be reduced at the cathode, and we will produce OH- and hydrogen gas. At the anode, we would typically expect water in a dilute sodium chloride solution to react. However, in brine, the concentration effect alters the position of these two on the electrochemical series. So instead of getting water, chlorine is actually going to react. We're going to get chloride ions reacting, and we will produce chloride gas. So Cl- reacts in preference when it is highly concentrated. So we get 2Cl- going to Cl2 gas plus 2 electrons occurring at our anode. And this is important to remember, this effect of concentration, remembering that the electrochemical series is at standard conditions, 1 molar solutions. If we increase that concentration, as we do with brine, up around 6 molar, we see different reactions can now occur. And this is one of the most common ones for you to remember for exam situations. So for the production of chlorine, it's in a membrane cell. So we have a semi-permeable membrane in here. Again, this is to separate the products, because if the products come into contact, they will react. What the membrane does allow for, though, is the passage of sodium ions. Remembering that as I remove chloride ions out of this solution, the charge will change. The sodium ions are able to move across this membrane into the other cell, balancing the charge in a similar way that the salt bridge does in a galvanic cell. So over time, we can add more brine in. We get Cl2 gas, which can be tapped off. As the concentration drops, we can take the spent brine out. Sodium hydroxide builds up in our negative cathode reaction. And we can tap off the hydrogen gas for use elsewhere, and the formation of sodium hydroxide means that that can be tapped off as well. So our two equations coming together for our overall equation is 2 water reacts with aqueous chloride to produce hydrogen gas, hydroxide ions, and chlorine gas. These coming from the 2 half cells of the electrolytic reaction. The last way that we can look at application in industry is the electro-refining of copper. This means that when we largely mine copper, it's impure. We refer to this impure type of copper as blister copper, and it will contain about 2% of impurities. These can include sulfur, iron, antimony, silver, gold, other metals. We purify blister copper by electrolysis in the presence of sulfuric acid, so this is in acid conditions. The blister copper is the anode, okay, and then we use a pure copper sheet as the cathode. So as the reaction will proceed, copper ions are at the anode. They are oxidized to produce copper ions. Copper ions from the solution at the cathode will be plated onto the cathode, which means that because this was a copper bar, we now, when we pull this cathode out of the cell, we are going to have 99.9 or 99% pure copper also being plated onto that copper bar. In the cell, other things can be oxidized. These include nickel and zinc. These are more reactive than copper and will oxidize and be soluble in solution. However, copper will be the strongest oxidant and therefore reduced in the cell first over these ones. So as long as there is copper in the cell, these 2 ions will remain in solution. The other impurities, such as silver and gold, are less reactive than copper, so they stay solid, aren't oxidized, and form a sludgy slurry at the bottom of the anode, which can be reclaimed after the process and sent on to further refining to pull out those copper, silver, gold, and other precious metals from it. So the ions that are more reactive than copper are also oxidized, but they stay in solution. Copper is preferentially reduced at the cathode, and then the ones that are less reactive than copper are gold, and silver form a slurry at the bottom of the cell. So these are the three main types of thing that we see. We have three processes. We have the molten electrolysis of a molten salt. We have electrolysis of an aqueous system, like we saw with the production of chlorine and sodium hydroxide. And we have the electroplating or electrorefining. We will learn more about plating after the stack when we've actually start looking at Faraday's laws. Electrorefining. So in this one, we want to collect the product from the cathode. With the aqueous solutions, we need to look at competition and concentration because of the competitive reactions with water. And then the molten salts, there's no water present, and remembering they are at much higher temperatures. So all our electrolytic cells convert electrical energy into chemical potential energy. They carefully select the electrodes. Generally, the electrodes will be inert, but it doesn't matter what we put at the cathode will always be inert because it's the site of reduction, so the cathode will never react. When we're designing our cells, we need to consider transport, location, access to energy, and our reactants and how we will transport our products. And then remembering that energy is expensive, so things like molten salts, being able to maintain those high temperatures make them more expensive. So things like our aqueous cells are a lot cheaper to run. Okay, remembering that we generally have to separate the products, but we don't have to separate the reactants for an electrolytic process. Hopefully this makes a little bit of sense. There are more examples for you to have a look at with questions on page 251 of your textbook, and I'll see you in class.